Okay, we want to address the question of how to get from the first orbit to the second. First orbit being at distance r1, illustrated here. Second orbit somewhere out here. So let's say we're here in the orbit and we decide to burn our rocket engines for a short time and deliver an impulse, F delta t. Okay, F being the force, a vector force which has a direction, the delta t being the time during which we exert that force. And of course, this F delta t is going to be a vector, and it's going to be equal to the change in momentum. So in doing this F delta t, we're starting with a velocity v sub I. This velocity here, our velocity of the orbit, this velocity squared, this speed squared divided by the radius is equal to the acceleration gravity produces in the direction of the planet. Okay, so there's centripetal force equals gravitational force, and this v satisfies that, so that this is consistent with a circular orbit. Now, having delivered this impulse, we're going to get a change in velocity which is equal to the impulse divided by the mass, with a caveat that the mass might have decreased. Well, the mass will have decreased if you burn fuel, but let's assume that decrease is not too significant, so that we have this. If the mass decreases very significantly, our delta V will actually be greater than it would be if we used the original mass, because of course we'd be using an average mass that's somewhat lower. Okay, so we get a delta V in any case. So we're moving tangent to the circle at the right velocity for a circular orbit. We burn the rocket, and we fire the rockets, and we get a change in velocity here, giving us a final velocity. Now VI and VF are before and after the burn. Okay, now VF is going to start changing, as we'll see in a minute, almost immediately, but this is immediately before, immediately after the burn. We assume the burn requires a very short time compared to the time required to do an orbit. Okay, so what happens? Well, picture here, the satellite is here, we got the force of the gravity here. This vector, and we've now got our velocity vector. Now I've sketched this dotted line here perpendicular to the radial line, in other words, perpendicular to the line of the gravitational force. And as we've seen, the velocity vector, due to this impulse, will turn from the tangent outward, okay? So that this vector is no longer perpendicular to this vector. Now, a couple of things to observe about this. First place, the kinetic energy that we have immediately after the burn is greater than the kinetic energy before the burn. Remember that if we want a circular orbit, we got to have just the right kinetic energy for that particular distance, for the particular radius of the orbit. We no longer have the right kinetic energy. We have too much kinetic energy, so we're not going to be in the circular orbit. So that's what we're saying here. The other thing is that each of these vectors has a non-zero projection on the other. Okay, the velocity vector has a non-zero projection on the gravitational vector, and we interpret that by saying that V parallel is not equal to 0, and by parallel we mean parallel to the force. It's also in the direction opposite the force, which means that any displacement that we have over whatever time interval, and we choose a time interval small enough that this velocity will not change too significantly, that any displacement we have is going to be in this direction. Well, the component, the projection of any displacement we have will be in the direction opposite the gravitational force, meaning that the gravitational force will do negative work on the mass, which is going to tend to slow it down. The satellite's going to slow. Also, observe that the force has a negative projection on the direction of motion, and you can think through the implications of that. So Going to have to get another board up here. So we'll pause for a second and we'll continue.